Sir, can you hear me?
Yes, Professor. Yes, Professor.
Good morning, sir.
Morning, very good morning, Professor.
Sir, can you just check your audio and video, sir?
Professor?
Oh, he's there. He's there. Can you check your video, sir, if you can? It's not.
Make it as a panelist. Accept the panelist.
Okay, I have to
Yeah, accept as a panelist.
accept it. Fine, fine. So, can you check your video and audio if both are okay?
Professor, can you able to hear me?
Yes, sir. Yes, sir. It's loud and clear.
Very good. Thank you, Professor.
Sir, you can just share your presentation. Just you will check it, sir.
Can I share the PPT?
Yes, sir. Yes, sir.
Is it visible now, Professor?
Yes, sir. Yes, sir. You can just zoom it, sir.
Professor, just another 2 minutes, right?
Yeah. Yes, sir.
I'll join.
You can put it in full screen. That's. Hmm. No, well, you're there. Fresh ആയിട്ട് വരാം. ഓ വരണോ? Sir, shall we start, sir?
Just a minute, Professor.
Yes, sir.
Okay, Professor, we can go.
Thank you, sir. So, very good morning to one and all present here. So, today we are at the day 4 of the Faculty Empowerment Program on Additive Manufacturing. So, we have in our midst Dr. V. Mugindran, Assistant Professor, Senior Grade, Department of Production Technology, MIT Campus, Anna University. Sir has had a very is an expert actually in the field of the additive manufacturing, as he has its exhaustive CV, and his areas of specialization are meterforming, optimization, image processing, finite element analysis, or two. And sir has been a member in various professional bodies like life member in Indian Institute of Production Engineering and a life member of Indian Society of Technical Education. Sir has been published in various journals of international repute, and also has papers published in various international conferences. He has been a coordinator for national level short-term course on FDP on CME 339, additive manufacturing, from February 24 to 10th February. So without any ado, I will now request the sir to take over, sir. Sir, it's all yours.
Professor, can I continue?
Sir, it's yours, sir. Stage is yours.
Professor, can you able to hear me?
Yes, sir, loud and clear.
Some voice disturbance, some unstable internet connectivity is there, I think, right? I can't be able to hear you. Is my voice very clear to you?
Yes, sir, very clear. You can go ahead, sir.
Okay, very good morning to the participants as well as the organizers. First of all, I thank Dr.M.G.R. Educational and Research Institute, Department of Mechanical Engineering, for providing an opportunity to present my research on additive manufacturing in this forum. And I belong to Department of Production Technology, MIT Campus, Anna University. And my specialization is metal forming. And now I am moving towards additive manufacturing. In this, we have selected this polymer-based additive manufacturing, where we can able to find some applications in medical devices as well as some what we call it as electrical panels. So with this introduction, I try to start my presentation. Can you able to hear me, Professor? No problem in that, right?
It's clear,
sir.
Clear.
Very good, very good. Thank you, Professor. So we talk about additive manufacturing, and you know very well, additive manufacturing is building of uh, layers. Just a minute. So it is a layer by layer process. So if you want, why we are going into additive manufacturing, here the wastage of material is somewhat less compared to that of subtractive manufacturing, right? So we will have one video here before starting this additive manufacturing. I think how to share my. Just a minute, sir. Wait, just a minute, sir. We can have one, I think, right? So Okay, so we can classify uh, uh, additive manufacturing by these 7 divisions. So VAT photopolymerization, material jetting, binder jetting, material extrusion, as well as powder bed fusion, and sheet lamination and direct energy deposition. So each classification has its own what we call it as type of melting the polymer and making some additive manufacturing examples, right? And some always this standard of ASTM F42 is followed in case of additive manufacturing. So our topic is liquid based additive manufacturing. Here we are going to see about 2 types of additive manufacturing. One is VAT polymerization, another one is material jetting. So in case of VAT polymerization, the resin is filled in a tub, which is photoresin, and you can see here, the resin is filled is in this particular tub, and there is a platform where we are going to build our part, and the photoresin is cured by means of this laser pointer, and you can see the laser pointer here. And once the laser is pointed out at a particular point, it tends to cure that particular point, and the laser tends to move in all these particular directions. Once this layer is cured, automatically the Y platform tends to move in the downward direction, and the resin is filled in the topmost layer. You can see here. Once this tends to move, the platform tends to move in the downward direction. The resin tends to fill the cured area, and again the laser is pointed out depending upon the designed prototype, and the prototype is obtained in case of VAT polymerization. In case of material jetting, the same, there is a build platform, and we can see elevator. The elevator tends to move in the downward direction, and you can see a leveling blade which is required to level the resin over that particular surface. And there are 2 materials. One is belt material, another one is support material. And if some orientation is required, right, this support material is required. For example, if you are building a prototype in this particular direction, there is no need of what we call it a support material. If you are going to build in vertical direction also, there is no need of what we call it a support material. But if you try to build your part in some inclined manner, right, say 45 degree, 60 degree, or 30 degree, like that, then the support material is required. So for this, we are having 2 types of head, right? So this becomes what we call it as a support material, and this becomes what we call it as a build material, right? So 2 types of material is required. One is build material, another support material, and both the materials are sent through what we call it as printing head, right? This is printing head, and depending upon the requirement, the printing head tends to switch and supplies the build material as well as the support material, and the object is somewhat cured, right? So this is in case of what we call it as material jetting. Another one is so we talked about VAT polymerization and material jetting. Now we talk about what we call it as photopolymerization process. So photopolymerization process is where the liquid polymers that react to UV radiation tends to cure and form a solid. So this type of reaction is what we call it as photopolymerization, where the photopolymerizes and the material used is what we call as photopolymers. So it is mainly used in what we call it as coating as well as printing industries. And stereolithography was the first type of wet polymerization process that was built by Charles Hull. So we talk about the photopolymerization process, how the liquid is converted into solid. So you can see some what we call as monomers here, right? And photo initiators. This is photo initiator, right? When this monomers and photopolymers, which is in photopolymer resin, is subjected to UV light, then the free radicals are formed, which tends to initiate a chain reaction between the monomers as well as photoinitiator, and the chain tends to propagate further due to continuous supply of this UV light, and terminates when all the monomers and the photopolymers are chained, thus creating a solid part. This is the what we call as chemical process that tends to happen behind this photopolymerization process. So on an average, right? So for every 2 photons that is created by UV laser, 1 radical will be produced, and that radical can polymerize over 1000 monomers. And once all the chain initiation completes, the polymerization process tends to terminate by means of what we call 3 types of process. One is recombination, another one is disproportionation, another one is subcollision. So here recombination occurs when 2 polymer chain merges by 2 radicals. So single radical is enough to polymerize over 1000 monomers. When 2 radicals come into contact, so it tends to terminate. This polymerization process tends to terminate. Another one is what we call as disproportionation. This involves essentially that cancellation of one radical by another without joining, and occlusion occurs due to the limited momentum. When there is no free flow of this radical, automatically the polymerization process tends to terminate. So if you go for the subsystems of liquid additive manufacturing, what are all the components that we are going to use in case of liquid additive manufacturing? One is what we call it as scanning system. Another one is the shape of the UV light, what we are using to cure the photopolymer resin. Another one, the shape of liquid that is used for this particular process. Another one, that build a direction, whether we are going to build from top to down or from bottom to up, right? So if you talk about scanning systems, the various scanning systems used in liquid additive manufacturing is, one is galvanometer, another one is flying liquid, another one is flying optics, another one is DLP mask, right? So if you go for the shape of the UV light, what we are going to is nothing but a single point laser beam and floodlight. The shape of liquid, what we are using in this liquid additive manufacturing is, one is wet, another one is jet, right? Wet is nothing but a single droplet, whereas jet is continuous droplet over multiple nozzles. And the build direction, you know very well, it is going to be either top down or from bottom to up, or in some cases, if necessity, we can go for some variable build direction also. So the scanning systems, what we are using in this liquid additive manufacturing, the galvanometer, you can see the laser is pointed out over this particular mirror, right? This is what we call it as mirror. And depending upon the design, right, the mirror may tend to change its orientation. So the laser beam tends to get deflected from these mirrors, and it is pointed out through a lens, what we call it as F theta focusing lens. So this pointer, when it tends to fall over this photopolymer resin, it tends to cure the resin, right? The whole arrangement is what we call it as a marking head, right? So here a single mirror is shown, but the galvanometer consists of n number of mirrors. This is the process that is happening in terms of galvanometer. If you go for flying liquid, right? So you can see a table here, XYZ table, where it can move in all 3 directions. Over this, the laser source is placed here, and this laser source is constant, it does not move, whereas this XY table tends to move over this particular surface. So this is what we call it as flying liquid scanning system. Another one is flying optic scanning system. This is same as what we call it as flying liquid system, but the XYZ table tends to be constant, whereas this there is no movement in z direction of this build platform, whereas the laser optic tends to move in the Z direction. That is the main difference between these flying optics as well as this flying liquid in case of liquid additive manufacturing systems. So another type of scanning system is what we call it as DLP. So in this, you can see here, there is a glass window. This glass window is made up of, again, this is what we call as mirrors, right? And each and every mirror can be controlled, right? So there is a, again, UV light tends to fall over this particular mirror, and it is directed towards this particular glass window, and there the photopolymer resin is placed over that, and this UV light tends to cure this photopolymer resin in case of DLP. In case of masking systems, n number of masks has been produced. So you can see here the opaque as well as transparent. So through this opaque, the UV light does not fall, whereas through this transparent, the UV tends to flow and it tends to hit the object. And this photopolymer resin, this is photopolymer 7 is what we call as photopolymer resin. And due to this transparent nature, the UV light tends to pass through these mirrors and tend to cure the photopolymer resin. Once the layer is built, you can see there is a table, right? This is what we call as table. This table tends to move down, admitting the photopolymer resin to flow over the, what we call it as the cured part, cured area, and there is a leveling scale tends to level the photopolymer resin over this cured area. Thus, the component is formed in case of liquid additive manufacturing, in case of DLP and masking system. So if you talk about the shape of the UV light, what we are using, two types of lights are using. One is laser beam, another one is floodlight. So it depends upon the nanometer what we are going to, micrometer what we are going to use, right? In case of laser beam, yes, a single point tends to cure a particular point, and this is what we call as floodlight. Floodlight, it tends to supply a beam of light over the surface of the photoresin and tends to cure, right? So if you go for the shape of the liquid, what you are using, one is vat, another one is jetting. You can see vat is filled over a particular tub, and the laser is pointed over the required area, and the vat is, and then the photopolymer resin is cured, and the object is formed. In case of jet, there are multiple nozzles, and we can go for different colors through these particular nozzles. It tends to go like a shower and tends to fill that particular area. Again, the laser beam or what we call as floodlight is passed over this particular photopolymer resin, and it has been cured in case of jetting. So we talk about a SLA, DLP, and LCD. And what is the difference between SLA, DLP, and LCD, right? So this also known as resin 3D printing. There are three main 3D printing technologies. One is SLA, DLP, and LCD. So all these three tends to use this light source. In case of stereolithography, we use UV lasers as a light source to selectively cure a particular polymer, photopolymer resin. But in case of digital light processing, we use a digital projector, right, where the UV light source cures a layer, complete layer of resin. But in case of liquid crystal display, we use an LCD display module for projecting some specific light pattern over the resin area, and it tends to cure, right? Now we can have a small video regarding the difference between this SLA and DLP and LCD printing, right? So I will share this particular. Just a minute. Just a minute, sir. I'll share. I can't go to look for it. Sir, my screen is visible, sir.
Yes, sir.
FDP, laser,
Audio is coming.
and LCD are the three main technologies.
Yes, sir. Yes, sir.
Three main are the
Sir?
and LCD are the three main.
Sir, you can slightly increase the volume, sir.
Whether audio is coming, sir?
To understand how they work, we need to know
Yes, sir.
how 3D printers see 3D models.
Sir, if possible, try to increase the audio a little bit, sir.
Yes, sir. Yes, sir. Yes, sir. Just a minute, sir.
DLP, laser, and LCD are the three
Are you
main
able to use
technology
the
types for desktop
audio,
3D
sir?
printing
Yeah,
Yes, sir.
perfect, sir.
in dentistry. To understand how they work, we need to know something about how 3D printers see 3D models. When you send a 3D model to your printer, the software slices it into hundreds of two-dimensional layers. Your printer sees a print as hundreds or thousands of these image layers that it will print one on top of the other until the model is complete. The chemistry of 3D printing resins means that each printed layer sticks to the build platform but not to the resin tank. Once a layer is complete, the build platform lifts slightly and then a new layer is drawn atop the previous. This process repeats over and over until eventually the models are completely built. Although DLP, laser, and LCD all follow the same basic process, they differ in how they deliver light to the photopolymer resin, and this divergence makes all the difference. Let's take a closer look. DLP printers use a light projector, similar to what you would find in a movie theater, to project the image of an entire layer simultaneously, regardless of the number of parts. Because they carry a full layer in a single flash, DLP printers can be outstandingly fast. They are also very reliable with low complexity and no moving parts. SprintRay Pro is powered by a DLP projector of our own design, enabling it to 3D print models quickly and with outstanding accuracy. LCD printers use a screen, similar to the one on your smartphone, to project the image of an entire layer at once. In this way, LCD printers are quite similar to DLP. They can even share materials. But LCD panels have a few key drawbacks. The light used to cure resin is damaging to the organic compounds in LCD screens. Therefore, most LCD printers treat their light source as a consumable, requiring frequent, costly replacement. Laser printers use a pin dot of high-intensity light to draw each layer. This process is similar to using a fine-tipped pencil to draw on paper. The laser rapidly moves across the resin tank, drawing the details of each layer as it goes. The laser must fill in the entire area with a pin dot of light, which limits the speed of the printer, especially when printing multiple parts at once. DLP, laser, and LCD printers are all used in dentistry, but the speed, simplicity, and durability of DLP has made it the first choice of dental professionals all over the world. Interested in learning more?
So we will go to our presentation. So this is the main difference between SLA, DLP as well as LCD differences. In case of faster curing, we go for DLP, whereas in case of accuracy, we go for stereolithography. So we talk about stereolithography. So writing, we are going to write with light. So it was patented in the year 1986 by Hull, and it was the first 3D printing technology. It is widely used 3D printing technology and most popular in case of resin type of printing technology. So this process is very accurate, isotropic as well as watertight, and the components obtained through this particular process has a finer surface finish. And it tends to create objects selectively curing polymer photopolymer resin, and it tends to use UV laser beam. The material used in case of SLA are photosensitive thermoset polymers, which come in liquid form, and when cured, it tends to form into a solid. So what are all the subsystems in case of SLA? So here SLA tends to use the galvanometer, and the type of light which SLA is using is laser beam and with the wet liquid, and the build direction in case of SLA is negative Z direction. So this diagram shows the stereolithography process. So this one is what we call the printed part, and you can see this becomes what we call it as the galvanometer. This is galvanometer, and the light tends to emit from this laser source pipe. This is laser, so the light tends to emit from this laser, and this galvanometer has tiny mirrors which tends to direct this laser light to the required area through this XY scanning mirror. This 7 is what we call as XY scanning mirror, and this scanning mirror tends to tilt in different directions depending upon the requirement, and there is a leveler which tends to level this resin over this print platform, and the laser tends to cure this required area. Once it tends to cure the required area, it tends to move in the Z direction and allowing the resin to flow over the cured part, and again the next layer tends to build. Here fine layer thickness can be controlled using this stereolithography process. So the model of the build material is shown in this particular diagram here. So working principle very well known. So it tends to position the build platform in the tank of liquid photopolymer depending upon the layer thickness. So a UV layer tends to cure the selectively curing area and tends to solidify the photopolymer resin. The laser beam is focused through these tiny mirrors which is present in the galvanometer. The whole cross-sectional area of the model is scanned so that the produced part is fully solid. So this galvanometer tends to move here and there, and according to that, the part is cured. So during this solidification, the monomer carbon chain that composes the liquid resins are activated by means of this UV laser, and the resin becomes solid, creating a strong unbreakable bond between the monomers as well as the photoinitiates through these particular radicals. So after printing, the part is not fully cured state, so it requires further post-processing under this UV rate, UV light, if very high mechanical strength is required. So the photopolymerization process is irreversible, and there is no way to convert the SLA back to their liquid form. Eating these SLA parts will cause them to burn instead of melt, right? So proper post-processing knowledge is required in case of this SLA printed 3D parts. So the types of SLA is based upon the machine setup, right? So two types of SLAs are there. One is top-down printers, another one is bottom-up printers. So in top-down printers, the laser source is placed above the tank and the part is built facing upwards. Whereas in case of bottom-up printers, the laser source is placed under the resin tank and there is a transparent part under the tank, and due to this the part is built upside down. So the tank has a transparent bottom with a silicone coating, and this silicone coating tends to let the light source fall into the resin so that the part is cured, right? So once the part is cured, right, the part has to be peeled from the what we call it as this build platform. So this is what we call it as the peeling step. Post processing step is what we call it as the peeling step. The bottom up orientation is mainly used in what we call as desktop printers. Palm Lab tends to use these types of printers. It is easier to manufacture. These bottom up SLA printers are very easier to manufacture and operate, but their build size is limited. We can't be able to go for large size in case of this bottom up SLA printers. So this is because the force applied on the part during the peeling step might cause the print to fail. On the other hand, the top-down printers can scale up very large build size. Industries are mainly using these top-down printers because a large model can be printed in case of these top-down printers. So the advanced capabilities of this scheme comes at a higher cost. Once the what we call as a level of accuracy tends to increase, automatically the cost of the machine also tends to increase. So we can able to compare advantages. In case of bottom up, it is going to be lower cost and widely available. But in case of top down assembly, we can able to build very large size prototypes and faster build times. If you go for disadvantages, bottom up has small build size, small material range, whereas it requires more post processing because support is provided in case of this bottom up. Whereas in case of top down, the cost is going to be somewhat higher, and a specialist operator is required in case of this top down assembly, and changing of material involves we have to empty the old tank and again we have to pour the newer material into that tank. So popular SLA printer manufacturers are Palm Labs in case of bottom up, and in case of top down it is 3D systems. So the build size is given, the typical layer height that plays a vital role, and we can able to obtain from 25 mm to 100 micrometer in case of this bottom up, whereas 1500 cross 750 cross 500 can be obtained in case of this top down assembly. Sorry, 225 to 150 micrometer can be obtained in case of top down assembly. So high accuracy can be obtained in case of top down assembly up to plus or minus 0.1% of the layer thickness. So materials, right? So in case of SLA, we are using liquid resins, which can be chosen based upon the end use of the part, what type of usage of the part. According to that, we can select the resins, right? The price of the resin tends to vary from $50 per liter to $400 per liter, depending upon the quality of the material. So industrial system offers a wide range of materials than desktop SLA printers. So SLA materials are more brittle than materials provided with FDM, SLS, and for this reason, SLA parts are not usually used for functional prototypes that will undertake significant loading. Wherever loading comes into act, we can't able to go for this SLA because it is more brittle than other materials. So some common materials that are used in case of SLA is used here: standard resins, high detail resin, clear resin, castable resin, tough or durable resin, high temperature resin, dental resin, and flexible resin. And the characteristics of these resins are given here, right? So what are all the printing parameters that has to be considered in case of SLA 3D printer? First comes the laser height. So laser height is the exact height of each cubed layer that is required. So it not only affects the speed of printing, but also the quality of curing also in case of this layer thickness. So the number of layers required to create the object determines the printing speed and the printing time. The thinner the layer, the longer the time for printing and cure and lesser the time for curing. The layer tends to range between 200 to 100 microns. A layer of 100 microns is suitable for most common applications. Next printing parameter is the exposure time. How far the surface is exposed to the either the laser light or the UV light. So light power and the curing exposure time plays a vital role in case of this quality of 3D printing. So exposure time is amount of time that has been the resin exposed to the laser light or UV curing light. So the default is around 6 seconds for most resins. If you want enough strength, the exposure time is somewhat increased. So increase in the exposure time, if the raft won't stick to the build plate. Generally, the longer the bottom exposure time, the more tightly thereafter will stick. So we have to go for peeling of the component from the what we call it as the build platform. So lift speed. This refers to the speed at which the build plate is lifted from the resin bed between the layers. If the lift speed is too fast, the model will be broken. So we have to go for the lesser lift speed. So the default lift speed is around 65 mm per minute. Next parameter is what we call it as support structures. So whenever inclined parts are built, their support plays a vital role. So you can see here, there is a human body which is printed here, and this tends to form the support structure. Right? Different types of support structures are there. Easily removable, easily solvable. Depending upon the requirement, we try to select the support structure. So the raft forms the base. This is what we call the raft, right? The raft forms the base that adheres to the build platform. Scaffolding stems from the raft to secure your part as it prints, right? So this is build material. This is support material. This is build material, and this is going to be the support material. This portion is the support material. Touch points are areas of contact where scaffolding meets the model. So not providing your model with enough support can cause misaligned layers, partially curing resins. The model to detach from the report supports. Once it cures thoroughly, this raft tends to cure thoroughly. It tries to build a stick over the build platform, and the removing of this rod plays a vital role. Thin walls are fuses to wrap the model to form as a pancake on the bottom of the resin tank. So careful selection of the support structure plays a vital role in case of SLA 3D printer. Another one is curling and wrapping. You can see here. So we are trying to build the bottom layer over this particular build platform, but one portion of the build part tends to stick, whereas other portion tends to come away from that build platform. This is mainly due to improper curing of the photopolymer resin, right? So one of the biggest problems relating to accuracy of the part produced by SLA is what we call as curling. Curling is similar to wrapping in FDM, and during this curing process, the resin tends to shrink slightly when it is tends to expose to light source, and this tends to create large internal stresses, developing the shrinkage or curling between the build platform and the first cured layer. Support is very important to help the anchor at risk sections, and part orientation and limiting large flat layers are also very important. So over curing module exam, we try to come away from the build platform. So care has to be taken while what we call it as designing the layer thickness that is required to print first to be sticky over that build platform. So we talk about the design procedures that has to be followed in case of SLA. So minimum supported wall thickness is required, right? So The recommended minimum wall thickness is 0.4. If it goes if it goes beyond less than 0.4 mm, right? So we can the wall will break. If it goes beyond what we call it as a supported wall smaller than 0.4 mm may wrap during the peel of this particular process. So we have to maintain a minimum wall thickness of 0.4 mm while using this SLA. So minimum unsupported wall thickness recommended is going to be 0.6. So an unsupported wall is that one connected to the other walls and fewer than 2 sides. So if it is smaller than 0.6 mm, again it may wrap or detach from the model during printing. So we have to maintain a minimum what we call as wall thickness of 0.6 mm if you want to avoid the wrapping of that particular wall. So maximum unsupported overhanging length, it should be what we call it as 1 mm. If it goes beyond, automatically what will happen? The structure won't be designed, structure won't be as per design. So that overhanging plays a vital role in case of this SLA. Right? And the inclination level will be a maximum of 19 degree from the level. If it goes beyond that, we can able to build, but the support structure is very much required in case of this. So printing flat surfaces at an angle plays a vital role in case of this SLA. Another one design guideline is what we call as maximum horizontal support that is required is 21 mm. Recommended is 21 mm. If it goes beyond, again, what we call it as a deflection from the support is happening. So if it exceeds, so we can able to get a surface like this, right? A part like that, it won't be straight, right? That is the what we call it as problem in case of SLA. So we have to maintain a maximum of 21 mm. So minimum vertical wire diameter in case of SLA it is going to be 0.3 mm. If it goes beyond this, it will again wrap, right? For a height of 7 mm tall and 1.5 mm for a height of 30 mm tall. So if it is less than this, what will happen? It tends to wrap, right? It tends to wrap like this. We can't be able to build a straight vertical wire diameter in case of SL. So, what is the minimum embossed part that can be built in case of SLA is the width of 0.1 mm. That is the maximum embossed, the minimum embossed. If it goes beyond that, we can't able to build it, right? So, the minimum engraved part what we can build in case of what we call it as SLA is going to be 0.4 mm. So we have to maintain a 0.4 mm engrave. If it less than that, we can't be able to build. So one material tends to flow over another material in case of this engrave. So the minimum clearance that is recommended in case of SLA is going to be 0.5. If it is less than that, automatically 2 resin tends to stick over there. So the minimum mold diameter that is recommended in case of SLA, it is going to have a 0.5 mm. We can't be able to build a part with less than 0.5 mm hole in case of SLA. The minimum drain hole, you can see here the drain hole is there. Again, it is 3.5 mm. And if it is less than 3.5 mm, what will happen? Automatically, the hole will close due to this UV. So what this how this SLA is used, we can see through these case studies. So a bladder device has been printed using this SLA for drug delivery. So for treating diseases in the bladder, which include interstitial crisis, bladder pain, bladder cancer, and existing treatment for it include oral medication, so transdermal patches, and intravascular illustrations. So here you can see here a bladder device has been built through this SLA, and this bladder tends to carry a 0. It has been built. There is no what we call it as it is hollow. the medicine is not filled into that, right? So here you can see 10% drug loaded. So difference you can able to watch here. So this is by means of hollow bladder device. So 3D printed solid bladder device, it has solid 10% loaded device, and this is a 50% loaded device. So these type of devices for medical treatment can be built through this SLA printing process. And 3D printing material here used as elastic resin from Formlabs. And in this case, the 3D printing material used is again elastic resin from Pointlex, plus along with some lidocaine hydrochloride monohydrate. So this is used to cure the disease that is provided in the ladder. Another one is what we call it as dental implants, which can be created through SLA. So you can see here the dental guides that is fabricated by means of SLA. So this can be placed in most ideal location, as well as angulation and depth, so that to get a clear what we call it teeth. So they are usually made of clear acrylic material is used, right, for transparency. So the material used here is dental SG. Another case study is this. So the time taken for the aligners, right? Custom aligners, teeth custom aligners are. So depending upon the what we call it as type of curing, the scan time is 5 minutes, and the design is around 1 minute, and the printing depending upon the design as well as the loading of that, it is 19 minutes. So the total time you can able to see it is going to be around 45 minutes in case of Form 3B plus default setting and Form cure. And the time tends to vary depending upon the various curing settings as well as printing settings. So another case study in case of what we call it as birds. So you can see here, this is the actual what we call as hornbill bird. So that horn is somewhat what we call it as some cancer. This is affected by means of some cancer. So what researchers did, they tried to remove this cancer area. So they tried to scan this particular part, and you can see here the scanned portion of this particular part, cancered part, and again it has been printed by means of this 3D printing, and this cancerous portion has been removed, and it has been fitted by means of a 3D printer, right? So 3D printing has been used in the past to help these hornbills with cancerous growth on their cases. A Form 2 3D printer was once used to create the prosthetic beak for an Abyssinian ground hornbill. So now you can see the fitted 3D part on the pick of this particular hornbill. So different different case studies are there in case of SLA. So you can see here some ear scanning, right? So we can able to build what we call it as the earables by scanning the person's ear and scanning the required area. So we can able to build the snacks earable 3Ds as well as different solutions we can able to put. So the categories may vary by means of these earphones, hearing aid, as well as some protection aids. If you are going into some what we call the sounding area, we can able to protect our ears using this muffler. So for that we can able to scan, and according to our ear we can able to print the mufflers by means of this 3D printing. So some selected products can also be printed using this 3D printing. One is what we call as the earbuds. Another one is what we call as the backbeds, right? So you can see a lot of printed 3D printed parts where we can able to use in our ears depending upon the end users, right? So here the raw material what we are using is what what we call it as biomed clear vision. So we can able to reconstruct some monuments, right? So here, this picture shows the reconstruction of ancient cities. So the material here used is what we call it as some white resins from farm labs. That by this we can able to create some monuments also, right? So some 3D parts has been created. So you can see here, this shoe has been created by means of this triple cell technology, right? So different flexible materials, same material with the different what we call as densities can be used to print, right? So this is what we call it as flexible area, and this is this portion, the bottom portion is what we call as order area. So here we can able to build the what we call it as part by using different materials, right, with different densities, right? So here you can able to design and see, visualize how the parts will be according to that. The support structure can be designed and can be printed. So for pre-surgical planning also we use this SLA printers. So this is what we call as the human heart, which has been printed, and before operating we can able to see how we can able to perform the operation over this particular part. And this is what we call as the earbuds, right? Earbuds and some different what we call the 3D printed parts used for medication. And we can able to recreate the existing pieces also. So different color resins can be used and can be printed, right? So the accuracy of the printing mainly depends upon the thickness of this particular layer. So some criminal investigations can be also as done through this SLA. So once the part has been printed, right, you can see here, right, here. So the Ohio State University partnered with the local law enforcement to investigate a decomposed woman's body near the town of Dayton, right? First they tried to scan the decomposed body, decomposed face. Then using these 3D techniques, they used to fit different what we call it as, they used different facial reconstruction techniques and to predict who has and be able to predict the what we call it as the face of that particular dead body, and it was a woman's body. And from this they found right, who has been whose body that has been decayed, right? So this SLA mainly tends to help in case of what we call the investigation purpose also. So we talk about digital live processing. So what are the subsystems for DLP? So we go for the scanning system DLP and the floodlight, and the liquid here used is VAT, and it is in negative Z direction. So here also we are using photopolymer resin to print, but through a floodlight. Through a floodlight, we are going to cure the part and form the prototypes. It is very similar to SLA, and due to it, the curing entire layer at once. In SLA, we use laser, it tends to cure a single point, but in case of DLP, we are going to use a floodlight, where it tends to cure the whole area. If you want smaller area to be cured, then we go for masking. It is much faster than SLA because the whole area is cured at a single time, right? So what is the construction of a DLP 3D printer? You can see here the light source tends to fall over the resin. The resin gets cured. Again, the build platform tends to move either in minus Z direction or plus Z direction. And there is a sweeper which tends to fill the layer over which tends to fill the photopolymer resin over the cured layer, and again the curing tends to occur. So this digital light source tends to use what we call it as micro devices, where it can be tilted depending upon the requirement, right? So you can see build platform. There comes the light and tends to deviate from this micro mirror. and we can able to tilt the micro mirror up to 10 to 17 degrees so that we can able to create different prototypes. So how the SLA prints, once we require, this is the requirement, right? It tends to start, it tends to cure the first circle, then the second circle, then the third circle, and at last the 4 circles are cured. But in case of DLB, since we are using a floodlight, it tends to cure the whole area at a time, so we can able to get faster products in case of this DLB printers. So DLB advantage, time taken to print one cylinder is equal to time taken to print 25 cylinders. So at a time we can able to print, right? So these intermediate portions are what we call as masked from the layer. So this curing area is by means of transparent masks. So multicolor printing and multi-material printing can be done in case of this material jetting. So we will have one, what we call it as, we will have one video regarding this polyjet.
Polyjet is a layer additive manufacturing technology used to develop plastic prototypes from 3D CAD data. This rapid prototyping process uses inkjet technology combined with UV curable materials to quickly and economically produce highly detailed and accurate physical prototypes. Polyjet is one of the fastest prototyping processes available to develop high-precision physical parts and is ideal for smaller parts, appearance models, and master patterns. The Polyjet process begins by slicing CAD data into cross-sections or layers as thin as 6/10,000ths of an inch. The data is then transferred to the Polyjet machine, which begins constructing the object one layer at a time. Similar to how an inkjet printer lays down pigment, the Polyjet printhead deposits small amounts of ultraviolet curable material on the build platform, eventually forming a single cross-section of the part. An ultraviolet light attached to the printhead simultaneously cures the material as it is printed. Once a cross-section is complete, the build platform is lowered slightly to make room for the next layer. As the part is built, support material is added to give supplemental strength to fine structures and down-facing surfaces. After all of the layers have been created, the finished part is removed from the platform and cleaned. Although finishing is not necessary, a number of hand sanding and paint options are available through service providers such as Solid Concepts. Polyjet parts are well suited for quick, economical prototypes requiring exceptional detail, surface finish, and edge visualization. Polyjet is ideal for a wide range of industries, including medical, entertainment, consumer products, automotive, and industrial design.
So we will continue here. So we talk about material jetting. Sir, can you able to hear me?
Yes, sir. Hello.
No problem.
Hello, sir.
Yes, sir.
Yeah, this is Pawan, sir. I have one question.
Yes, sir. Yes, sir.
Sir, actually, suppose we are doing some operation in human body and suddenly we got some fracture in body and we want to replace some artificial like artificial components. So we can we can manufacturing immediately by additive manufacturing. It is possible.
Yes, sir. Yes, sir.
Like during operation time we can manufacturing it.
Yes, sir. Yes, sir. That is possible in case of this polymer prototype polymer resin printing, sir.
Okay, sir. Thank you, sir.
But in case of metal, it is somewhat very difficult, sir.
Okay, sir.
Okay, sir. We will continue, sir. So we go
Yeah.
for material
Yes,
jetting. So again, here we are using either flying liquid or flying optics in case of scanning systems, and floodlight is used as a light source, as well as here we are using Z, and only possible is in case of plus Z direction. Right, so it is similar to what we call it as the 2D printers. Here printing it is there, and multiple nozzles are built over this printing head. It tends to dispense the photosensitive material through these multi nozzles, and again we are using a UV light for curing this part layer by layer. Here we are using thermoset photopolymers, and high dimensional accuracy can be obtained through this multi-jet printing, and multi-material is also possible in case of this multi-jet material printing. And we can, for example, if you are going some visual prototypes and tool manufacturing, we can able to use this material jetting 3D printing, MJ 3D printing. So here you can use here you can see what we call it as here you, so it is not going. So here you can see the schematic diagram of this MJ 3D printing. So Stratis uses this technology for printing the particular prototypes. So how this tends to work? So the liquid resin is heated up to 30 degree centigrade to 60 degree centigrade, and small droplets has been jetted over the desired location. Again, a UV light source is used to cure these small jets, and once the first layer is cured, automatically the build platform tends to move one layer height. Thus the part is created. The same mechanism used in case of SLA is used in case of material jetting, and homogeneous mechanical and thermal properties can be improved in case of this material jetting process. So this is what we call it as a continuous mode. So the droplet from this, what we call it as fluid supply pump, tends to flow. So you can see the droplets are continuously coming down, right? So this is a substrate. The droplet tends to flow over this substrate, and the UV source is cured, right? For example, if you don't want, right, so this droplet will come here and it will fall over this particular substrate. It will be cured, right? And if what we call it as if some space is required, or a droplet should not fall on this particular space, what we try to use some what we call as droplet catcher, so that the droplet can be continuously the droplet cannot be continuously dispersed over this particular substrate. So this is what we call it as continuous mode. If you want to neglect one droplet, you have to provide one droplet catcher. But in case of this drop on demand, right? Drop on demand, this is the substrate motion, it tends to move. So depending upon the requirement of the droplet, the dry signal, the actuator tends to actuate this fluid supply pump, and according to that, the droplet tends to fall over this particular substrate. This is regarding what we call as drop on demand mode, right? So again, what are all the characteristics that is required in case of material jetting? So the layer height, again, the layer height plays a vital role in case of what we call it as the accuracy of that particular part. So in MJ, all process parameters are very preset, so we can't able to what we call to modify. It is manufacturer based. So even the layer height is linked to each specific material as its own layer height. So complex physics of the droplet formation has to be studied before using this material jetting. The typical layer height used in material jetting is around 16 to 32 microns. So accuracy is around plus or 1% in case of this MJ. So if you want most accurate 3D printing technology, then we have to go for this material jetting. And wrapping occurs in case of wrapping can occur, but it is not common in case of other technologies, right? So for this reason, very big parts can be printed with this material jetting with great accuracy. So the build size is approximately 380 cross 250 cross 200 mm. and as big as we can go up to 1000 cross 800 cross 500 mm. Support structures are always required in material jetting as in case of SLA, and supports are always printed on the secondary dissolvable materials, right? So this part is very, very important. The selection of support structure plays a vital role. So what we select in case of material jetting is dissolvable support structure. So multi-material can be printed in case of this MJ, and at the build area level, different parts can be printed in different materials, different colors. So this is mainly used for practicing in case of some operations, right? Surgery operations, when we are performing, we can able to scan the human part with the different colors, and it can be printed with different parts and different colors, and it can be operated before going for surgery, right? So that is mainly this material jetting is mainly used for pre-operating purpose. So if you want some glossary finish, right, matte surface finish, shiny surface, right, the thin layer is required, right? Thin layer of support material is added, and the glossy setting should be used when smooth shiny surface is desired. So the cost of printing in case of the shiny surfaces, matte setting tends to increase. The matte setting should be used when accuracy and uniform surface finish are required, right? If not, we can go for rough surface finish. So some of the common material that is used in case of this 3D printing is rigid opaque plastics, right? And in case of standard materials, simulates injection molded parts and brittle in nature. If we can go for some flexible materials also, like a rubber and some customizable hardness whenever required, we can go for this flexible material. We talked about one shoe, 3D printed shoe. There we can go for these flexible materials. Another one is simulated polypropylene. So whenever we require good flexural strength, we can go for this particular material. Another material used here is simulated ABS. So where high temperature resistance is required, we can choose this particular material. Another material, right, commonly used in 3D printing is castable. So here no ash after burnout occurs. That's why this is mainly selected. So high temperature material. So whenever temperature plays a vital role in that particular component, we go for high temperature material. And whenever some glossy finish, matte finish are required, we go for some transparent material. Glass-like appearance can be obtained, and it can be processed to 100% clear and medical grade. So whenever we go for some sterilizable requirement, there we can choose this medical grade, right? So biocompatible material, this can be used in some dental as well as medical applications. So advantages and limitations, whenever we talk about material jetting can produce smooth parts with surfaces comparable to injection molding. Parts can be created with material jetting, have a high homogeneous mechanical and thermal properties. The multi-material capabilities of MJ enable the creation of accurate visual and haptic prototypes, what we talked about in pre-surgical operations. So material jet parts are mainly suitable for non-functional prototypes. Due to poor elongation, this cannot be subjected to some tensile loads or what we call it as fatigue loads. So material jetting materials are photosensitive, and their mechanical properties degrade over a particular time, right? The cost of technology is very high, and it is not financially viable for some other applications. So you can see here, right? So this is hardened material, and this is flexible material. This portion is what we call as flexible material, both printed in the same machine using multi-jet, what we call it as multi-jet photosensitive material. The Ford diffuser is a lightweight running sneaker with the upper made of a prime knit technology, which is ideal combination for automating the footwear manufacturing workflow at Adidas. This upper color is a mix of black, pink, and orange knits. The main innovation of the Ford Diffusio is that the 3D printed midsole is also what we call it as multicolor. right? So multi-jet is mainly used for printing these type of components.
Sir, 1 second, sir.
Yes, sir.
That is the multicolor having like having a same path or have a different path?
Sir, this is a single product, sir, with
Okay.
single product with different materials.
Okay. Oh.
That's why we call it as multi-jetting.
Oh. Okay, sir.
You can see here some bottom portion is of hardened surface. There
Yeah.
you can see some what we call it as some uh, pores, right? Pore-like structures.
Yes. Yes. Yes.
That is for flexibleness.
Okay. There is a different color is there. So
Yes, sir.
that color is in mix same pot or they have different like
Different colors,
yeah.
different materials.
Oh.
So, Pepsi has invented some what we call the Pepsi is using this 3D printing. So this is what we call it as the actual injection molding part, and this is 3D printed part, right? So this is by means of injection molding, and this is by means of 3D printing, right? 3D printed part, right? So they can able to save, right? By utilizing the status J55, they can able to reduce up to $1,000, right? Previously they were using up to $5,000 to $10,000, but using this 3D printing, they can able to reduce the cost of this printing process, right? So some we talked about some pre-surgical components, right? You can see this particular part with the different what we call it as colors. So this can be pre-operated before going for actual operations, right? Okay, so this right. So this is injection molding, right? So they are creating a what we call it as chip, right? So we can able to reduce cost by using this 3D printing in case of by means of injection molding, right? And you can see some calipers that is required for raising has been printed by means of this 3D printer, right? So here we are using a status 3D printer to produce this particular caliper and produced in only 24 hours, so that the printing time is less in case of this 3D printer, whereas when compared to the conventional uh, casting or what we call it as machining process. In case of prototype brake caliper, absolute accuracy is essential. So they chose this 3D printing methodology to maintain that particular accuracy, right? So what we did in this liquid additive manufacturing, right? So we in MIT developed a low cost indigenous composite printers. We will talk about that, right? So the background of our case, we choose this additive manufacturing, and we selected this material extrusion technique, and we also selected this UV direct ink writing. So here various extrusion systems are shown here. So first one is plunger based. You can see the plunger here, right? This plunger can move up and down. So once it tends to move down, the material filled within the tank tends to flow through this particular nozzle. Another one is filament based, right? The FDM uses this particular technique. Another one is what we call it as screw based. So we tried this plunger based and screw based to build this particular model here, right? So material extrusion, our material extrusion method is, right, we used a pinch roller feed system. The filament material comes in this actual, right? We try to use some ultraviolet light and some increaser wire ink, and with this increaser wire ink and ultraviolet rays, we try to print part over this particular surface. So this is the what we call as Ender 3D printer, Ender 3D printer. What we are using in our lab, right? We tried to convert this Ender 3D printer into some photopolymerization printer, right? So we used some Blue Wave 200 Dynamax, right, controller, and we are using some UV curing, right? You can see some UV curing, right, which costs around $2,000. So this is the existing setup, right? and laser diode, it is around rupees 3,000 to 4,000. So we tried to replace these two by means of this laser diode. So what are all the components what we have used in our 3D printer? So we selected a motherboard MKS Gen LV1, and we used Ultimaker Cura software for our project, and we used a display MKS Mini 128.6 version 3, and we used Marlin firmware for building that particular development. Right. So the component of the UVD LV curing system. So for this, we used the UV LED holder and the extrusion system along with the holder and a nozzle shield to separate the what we call the flow of material from the nozzle from the UV light that is exposed over that particular nozzle. Right. So this is the what we call it as holder, system holder used for holding that particular extrusion flow. Right. So this is the nozzle shield what we have designed for our particular product, and this is the UV LED holders. Right. So different types of there. Right. One is what we call it as array type. One is array type. One is array type. Another one is what we call it as concentration type. Right. Another one is concentration type. These are all are patented. So we tried for a different component, a different arrangement like this. So we designed our own UV LED holder, and we tried to assemble. So this is the assembly of our what we call it as a UV curing system, and we have applied for a patent, right? IP 2023-410-75654, right? And it is under process. It is going to be approved, right? So this is our setup what we have built, right? So you can see the build platform, and you can see the nozzle holder, and you can see the UV light strips, and you can see the nozzle, right? So a connecting hose. So a increaser wire comes here from the top. So we used a peristaltic pump to supply the ink from the increaser wire to this particular nozzle, and you can see a UV holder here, right, which tends to support this UV curing system as well as this particular nozzle. To control the moving speed of this XYZ table, we used a speed regulator, and also at how much speed it tends to move, we used a speed display. Right. So what we have selected epoxy resins and cyclohexyl ketone. So this is the polymer resin we are used any cubic 3D printing UV sensitive resin, and here we have used fumed silica to thicken this particular resin, and polyvinyl pyrrolidine. This is used as a photo initiator for curing purpose. Right, so we conducted some rheological test over the printed parts, and we varied. We kept the any cubic photopolymer resin quantity as constant. We tried to vary the fumed silica with the weight percentage and also the polyvinyl pyrrolidine. Right, so we conduct a few experiments. This is the rheometer what we have used from the Department of Chemistry, CEG campus, Anna University, for studying the characteristics of this 3D printing. So here we have gone for the flow sweep test, and the results has been predicted. So we predicted, we have drawn a graph with respect to viscosity and shear rate. So you can see the zero. This is what we call it as zero weight fumed silica, right? The viscosity, the shear rate is steady, but the viscosity is same, right? When we use the fumed silica up to 5% weight, automatically we can able to see the viscosity tends to flow. That the actual flow rate tends to come down, right? And we also conducted some amplitude sweep test, right? And the results are shown here, right? So with 5% storage modulus, with 5% loss modulus, we can able to obtain a good flow rate in case of this rheological results. Right, so we selected a nozzle, right? A nozzle. The nozzle diameter is around 0.84 mm, and the length of the nozzle is around 35 mm. And we using this particular setup, we maintained a different standoff distance, and we varied the printing speed, and we varied the average layer width. Right. We varied the printing speed, and we with these two parameters we tried to print different, what we call it as different parts, right? So you can see the difference here. The SOD is 3 mm, the printing speed is 5 mm. From this, we try to measure the average layer width, what we are getting from the parts, and also the layer height, average layer height, what we are getting from the printed parts, right? From this, we try to optimize the printing speed and the standoff distance, and we also try to optimize the layer width and the layer thickness. And we also gone for this curing studies, what we call as FDR and chocolate extraction test. You can see the uncured resin here, right? And the cured resin for 120 seconds. So if you try to maintain the what we call as UV glaze for 120 seconds, we can able to obtain a proper curing, right? So this is the what we call it as, using these results we try to print different structures. So you can see a hollow cone formatting without any slumping here, and interesting, we try to print a hollow bend pipe formation without slumping, right? You can see here without support material, you can see the inclination of the part what we have printed through this developed setup. We didn't use any what we call the support structure here, and this is support my presentation. I thank the organizers who have given this opportunity for exploring my work over this liquid additive manufacturing. Is there any question, please? I will try to answer.
You can, participants, you can ask questions.
Any questions, sir?
Dear participants, you can ask questions.
Hello.
Yes, sir.
Yeah, sir, that Cura software is we are using for only 3D modeling design, right?
Yes, sir.
Okay.
Is there any questions, sir?
Actually, there is no question. Even in the chat, also, I'm looking, sir. Okay, I think there is. I think we can I would like to, from the onset, I would like to thank Dr. V. Mugendran sir for taking time out from his extremely busy schedule to come forward and present his research on liquid additive manufacturing, sir. I hope it was very interesting and very thought provoking, and it could also will motivate young researchers to take forward this work further. I think we have a question now. Mr. S. Balasubramani. We have a question, I think.
Thank you, Professor. Thank you. Thank you for giving me an opportunity.
Yes, sir. Thank you very much, sir. Thank you very much.
Can I close, sir?
Yes, sir. Thank you very much, sir. Thank you very much, sir.
Thank you.
Thank you.